Okay, so we have officially concluded our study of derivatives. We are now moving into and expanding our study to the second half of calculus, which is integrals. Integrals are represented by areas under a curve. So what we're going to do today is investigate finding areas under the curve using techniques from our past. So I always like to start with a thinking scenario. So suppose from the second to the fourth hour of your road trip, you travel with cruise control. Your cruise control is set to exactly 70 miles per hour. Assuming we're driving in Ohio and the land is flat, your cruise control speed should not change at all for hours 2 to 4. How far have you traveled during this time? Well, if you're traveling for 2 hours at 70 miles per hour, you've driven 140 miles. Sorry, 2 hours times 70 miles per hour. And we could know this or figure this out because we are able to cancel our units of hours, because this hours is in the denominator and the hours up here is in the numerator, which left me with miles. Sketch a graph modeling the situation in the example above. Geometrically, how do we indicate distance traveled? So if you think about back in the day, you had time and velocity. So this is like a velocity time graph. We have hour 1, 2, 3, and 4. And then 10, 20, 30, 40, 50, 60, 70. The only information we're given is our speed at hour 2, 3, and 4 is 70. And it is a constant speed. So our graph of our speed from hours 2 to 4 would be a horizontal line. And then if you think about this, what we are doing is finding the space below, which is represented by a rectangle, and the area of a rectangle is the base times the height. In this case, base is 2, height is 70, once again leading to 140 miles. What if the velocity was not constant? So say, for instance, the velocity in miles per hour is given by the function velocity equals 10t minus t squared, where t is in hours, and we wanted to know the total distance traveled during the first 10 hours. So if we sketched this graph, geometrically speaking, our graph would look something like this. At time 0, my graph's at 0. At v of 10, it would also be at 0. And my vertex would thus be at 5. So to know our max height, we would maybe want to find v of 5. So my graph is a parabolic curve. And it says, geometrically speaking, could I find the total distance traveled in the same way that we looked in the first example? Well, now the problem is that if I tried to do a rectangle, I would be left with all of this area not included in the area under the curve. So a rectangle would not be a good geometric. So where it says, would that be a good way? The answer is no. A rectangle would be a terrible way to try to geometrically find the area under this curve. I personally think if I was going to try to find the area under this curve based on the shape of it, a triangle on each side would maybe be the best bet, because a triangle has an area represented by 1/2 base times height. So my base is 10 and my height is 25. So I get 5 times 25, or 125. And again, if this is velocity in miles per hour, that would mean they drove approximately 125 miles. What we're going to move towards, and a preview of what comes in tomorrow's lesson, is doing this as an integral. And as an integral, this would represent the time, 0 to 10, of the velocity with respect to time, where velocity and dt represent parts of the area. One represents your height and the other represents your base. And typically when we think about an integral, we're actually always making rectangles, which is what we're going to look into and discuss today with what we call a Riemann sum, which is a collection of rectangles. So the key to finding the total distance traveled in the last example to a method similar to the first example is to break that interval into shorter segments. Hence my hint towards making smaller rectangles. That the velocity over time becomes almost constant and those rectangles become infinitely smaller. If the velocity is almost constant for each time interval, then we can find the distance traveled for each time interval with these extremely thin rectangles and add all the areas of all the rectangles together. And I know that sounds simple enough, right? So this important calculus concept is called integration. We're going to be spending the next few weeks on this. And it turns out that the given graph of a rate of change, like velocity in miles per hour, will allow us to find the total distance over an interval. And that total distance represents the distance traveled, and we do this by finding the area under the curve. Our goal for today is to find that area under the curve using approximations known as left Riemann sums, right Riemann sums, middle Riemann sums, and trapezoids. So, to determine the area between a function, we want to look at the left Riemann sums. These are called the left endpoints. In order to find the left Riemann sum, we are going to plot our points on the left side. So here are my key points. So my area is from 0 to 2. So beginning to end. We broke it into 4 intervals because 0 to 2 breaks down nicely into 4 intervals. They also told me that n was equal to 4. So where it says the number of subintervals or rectangles in this problem, we'll use n equals 4. So to find the distance that intervals occur at, we're going to use a formula called delta x equals b minus a divided by n, where the b is how far out into your interval you go, the a is where you begin, and the n is the number of rectangles we're creating. So that makes my delta x 1/2 or 0.5. So my delta x is also like the dx or the dt in my integral equation. So the delta x or the dx is like my dt in an integral equation. It represents the width of my rectangles. So each of these have a width of 1/2. And then the second value, the 1, the 1.5, the 2, and the 3.5, those are all coming from the height of the rectangle on the left side of the rectangle, so where I have those black dots. So it's the height of the rectangle on the left side, and the value is coming from our f of x curve. So you're finding f of x at 0, at 1/2, at 1, and at 1.5 on the curve. Those f of x values that you're finding are the heights we're multiplying my widths by. So that we get an area of this first rectangle is 1/2. The second rectangle is 0.625. The third rectangle is 1. And the fourth rectangle is 1.625. Summing up all 3 rectangles, we get that the approximate area under that entire curve is 3.75 units. Like our linearization, this curve is concave up and increasing. Since it's concave up and increasing, all of my left Riemann sums are going to be under estimates. So that 3.75 units is an under estimate. A right Riemann sum is going to give you a different type of estimate. So let's do the right Riemann sum almost together. My delta x is staying the same because my interval is the same, my subintervals is the same. So my delta x remains 1/2. So I'm going to draw in each of my rectangles. But now my rectangles are coming from the right side of the curve. So what you'll notice about each of these rectangles is that the areas are all over the curve. So this right Riemann sum is going to give me an over estimate. What's nice is we previously found f of 0.5. So I'm going to take my 1/2 and I'm going to multiply it by each of my heights. So you take f of 0.5, so that's 0.5 squared, which would be 1/4. 1/4 plus 1 would be 1.25. You're going to take 1/2. You're going to plug in 1. 1 squared is 1. 1 plus 1 is 2. 1/2. Plug in 1.5. And you get 3.25. And plug in 2. And you get 5. And then what we're going to do is sum up each of those values. So that this time I get a total of 5.75 units. So that represents the area under the curve. And we can tell that that is definitely greater than our left Riemann sum. So we call right endpoints a right Riemann sum. You'll hear me refer to this as RRam. So let's keep going. Using a midpoint, or MRam, this one's probably the most tricky because now I have to find all new height values, and I find each of those height values at the midpoint of each of my widths. So the width is 0.5, the midpoint is 0.25. The midpoint of 0.5 and 1 is 0.75, so on and so forth. Now, if you compare the rectangles from the left to the right to the middle, in terms of this code, it appears that this equation is going to have the best approximation using the midpoints, because the midpoints seem to have an equal area over and an equal area under. So the approximation in this case should be the closest to the actual. And every equation and formula is going to have a better one depending on what the function curve kind of looks like. So all three of these methods are known as the rectangular approximation methods, aka a Riemann sum. They allow us to calculate the area of a region bounded by a curve, the x-axis, which is super important, and the lines x equal a and x equal b. As we previously discussed, the width is determined by the subintervals, and the height of each rectangle is determined by the function value at a point in the subinterval. So my interval is a to b. The width or base is represented by delta x or dx. And then the height comes from the function value at the x or dx width for that spot. typically I break this over into a few days, or I give that video at the end of a unit or test if our test is on a Friday. Because of our test being on a Tuesday, we're just going to do 5.1 in one day. So which RAM method is shown in the graph below? So if you look at the graph to the left, you want to look at where each corner is meeting the graph. So when I look at this graph, this corner meets the graph, this corner meets the graph, and so on and so forth. Since all of my corners meet the graph on the left side, this is a left Riemann sum. We want to look at the second graph, identify the corners that are meeting the graph, and once again, these are all on the left, making it a left Riemann sum. And then it says, is graph A or graph B a better approximation of the area under the curve? Well, guys, graph B is the best approximation for the area under the curve because it has more rectangles. The more rectangles you have, the closer your areas are going to be to the actual area under the curve. So B has the better approximation because the rectangles have smaller widths, which increases the number of rectangles, giving a better approximation. Okay, suppose the odometer on our car is broken. And we want to estimate the distance driven over a 30-second time interval. We take speedometer readings every 5 seconds. Now, what is important and something that happens a lot is the time is in seconds, but the velocity is in miles per hour. So we need to convert our velocities so that we can get these to be in the same units. So what you want to do is essentially change your velocity to feet per second. We could change it to miles per second, but that would turn all of my values into decimals. By changing it into feet per second, I'm going to be able to maintain whole numbers. So the conversion, which I'll give you the first two, I'm going to have you guys actually take a minute and try on your own, is that 1 mile per hour is equal to 5,280 feet per, 3,600 seconds. So you take 17, 21, 24, and multiply them all by that large fraction. So go ahead, take a minute, use your calculators, and convert the next 5 velocities. Okay, so you should have had 25, 31, 35, 43, 47, 46, and 41. So part A says, estimate the distance traveled during the time period by using the velocities at the beginning of the time intervals. If we're using the velocities at the beginning of the time interval, that's another way of saying, hey, do LRam. But now we're doing LRam without a graph. So LRam represents distance traveled using left endpoints. So what we're going to do is our distance traveled every 5 seconds, well, that 5 seconds is going to represent my dx, or my delta x. So my total distance, if you think about the way we used to do it, we would say, okay, our velocity times time plus our velocity at the second interval times time, velocity at the third interval times time, and so on and so forth. What's the same in this case is our time. So what we can do to make our Riemann sums a little easier is to factor out our time. So for the left Riemann sum in this case, my time is always 5. And then what I'm going to do is pick the velocities on the left side of the table. So I'm going to pick 25, 31, 35, 43, 47, and stop at 46. I'm not including 41 because that's on the right side of the rectangle. So when you're thinking about your sums, that 46 is here, that 47, or 41 rather, would be there, and we don't need that for a left sum. So adding all of those up and multiplying by 5, I get 1,135 feet. We want to compare that estimation to the estimation using the end of the time intervals. So that's a fancy way of saying the right Riemann sum. So my total distance equation hasn't changed. The time interval hasn't changed. What's changing is the values of the velocities that I select. So if I'm selecting the right sums, then I'm skipping the first velocity and adding up all of the velocities thereafter. You could also start at 41 on the right side of your table and get down to all but the last value. It doesn't matter which side you start on because addition is commutative. So whether we start at the right side of the table or we skip one and go from the left, we're still going to get the same answer. And we see that the total distance is 1,215 feet. It should make sense to me that the right sum is greater than the left sum, because when I looked at my values in the table, the initial velocity was less than the final velocity. So that made that made the rectangles higher, and since all the middle numbers were the same, so you're using the same middle values, you're just changing the endpoints, you can determine which one's going to be the over and which one's going to be the under by looking at your beginning and end values. This will be an over because it's higher, this would be an under because it's less. And then we have that suppose we want to enclose a region R formed by the function f of x and the x-axis between 1 and 3. So I'm concerned with the area from 1 to 3. We're going to create 4 subintervals, so delta x would be 3 minus 1 divided by 4. Use RRam, MRam, and LRam to estimate the area of R. So in order to use those points and essentially find my value, I need to know what is f of 1, f of 1.5, f of 2, f of 2.5, and f of 3. So finding each of those values would at least give me all my LRam and RRam values. So for f of 1, you'd have 3 minus 1, which is 2. So that means at f of 1, my parabola has a height of 2. For 1.5, you would have to take 3 times 1.5, which is 4.5, minus 1.5 squared, and we get 2.25. Plugging in 2, 3 times 2 is 6. 6 minus 4 is 2. And then plugging in 2.5, you'd have 2.5 times 3 minus 2.5 times 2.5, and you get 1.25. And then plugging in 3, well, 3 times 3 is 9, minus 9, giving you 0. So we can just kind of see from this graph that we definitely do not have symmetry. The vertex is between 1 and 2, possibly even at 1.5. Didn't do it yet, but that's where I'm thinking. So that our rectangles are definitely not going to be equivalent in terms of left ram and right ram. So my LRam is 1/2 because that's not changing. And we're picking the left endpoints. So 2, 2.25, 2, and 1.25. So 2, 2, and 2 gives you 6, plus another 1 gives you 7, and then adding up your 2.25s, you'd get 7.5, and then you have to cut that in half, which is 3.75. RRam is picking the right endpoints. So that would be 2.25, 2, 1.25, and then 0. So given that the last value in this case is 0, I can already say that my left ram is going to be my over, and my right ram is going to be my under. And then to find my MRam, I'd have to find the F values between each of those. So 1.25, F of 1.75, F of 2.25, and F at 2.75. So that would give me 2.1875. And yes, I'm using a calculator for these ones. So my MRam, same 1/2 width. And we get 3.375, which is almost right in the middle, if not right in the middle, of the MRam, or the LRam and the RRam. So if you averaged LRam and RRam, the average of those is 3.25, so we can see the MRam is 3.375, and in this case, once again, I'm going to think that MRam is the most accurate based on the shape of our curve.
And we said the units were just units?
Correct.
That makes sense to me whenever we were doing like velocity over time, because the units canceling out. But when we're just doing it normally, how come it's not units squared? Like when we're just saying it's x and y.
That's a great question. And I actually at one point wrote units squared and had scribbled it out because I feel like our textbook wrote units, and I don't have our textbook with us. But I agree with you sometimes that I feel like it should be units squared and that the velocity and the miles make sense. And we are doing area. But I swear our textbook calls it units. So let me look into that a little bit, because I have a feeling that I can't give you a truthful answer on that.
No worries, I was just curious.
No, I mean, it's a good question, and like if you, I don't know if you can even see it. Let me clear this out. Because some of our examples I like sometimes take from our book so that the homework matches our book. And if you look here, like look, I originally had units squared.
That's what made me think of it, to be honest, when I saw that, and then you scribbled it out, I was like, wait, why isn't it that?
I know. And when I was looking at it even on here, because I definitely went through and took it, and I was like, why did I scribble out the square? Because that would have been from last year. So I'm going to investigate, and I'll give you a more definitive answer before the end of the day today. I'm going to go look into, I have a pre-calc book here. I don't have our textbook here, but I can pull up some textbooks, and I'll give you a more definitive answer, I promise. Because I don't want to lie to you one way or the other. So, because it's funny is when you said that and you looked at it, I was looking at it on my end too, going like, why did I scratch out that squared last year? And like, I in my own head was just like questioning it the whole time. Because you're right, I agree to the feet. It makes sense. Miles per hour times miles, or times hour, cancel hours, leaves you with miles. But if you think about a rectangle, that's a unit, and that's a unit. So why isn't it units squared? So I'm going to investigate. Alright guys, so hopefully everybody is coming back. This is usually about the time we take our break on a school day. So hopefully anybody that left or didn't ask me a question is back now. On the AP exam, typically every year, we will be given a question similar to this, but the table is going to be involved with other questions. This statement right here is only going to be like part A or part C. It's only going to be one small segment. But I will say that in the last 5 years, there has always been a Riemann sum. It switches up between the left, the right, and trapezoid. I haven't seen a midpoint. That doesn't mean they couldn't use a midpoint. I just haven't seen one. Or if I did see one, it would be a little bit set up differently. So this example we have on this page, you can see in each part, I'm changing the number of subintervals, so that you can see how a table and the different subintervals changes your values. So it says, given the information in the table to the left, use a right ram with 6 subintervals to estimate the area under the curve. So my delta x is 12 minus 0 divided by 6, which gives me 2. So that tells me that each of my rectangles is going to have a width of 2. And this table is set up nicely so that each of them are equally spaced. We might have tables in the future that are not equally spaced, so then your delta x is going to be changing for each width of the table. A right Riemann sum means we skip the first, or if you think about the heights of the rectangles, I kind of drew the rectangles off to the sides. Each of those heights would come from this side of the rectangle, which starts with 5. And this would definitely be a non-calculator question. So you just go through and add up all your values. And again, if your mental math skills aren't great, subgroup them into 2s. And then go and sub them, into your final value. So 13 is 26, adding 11 more, we get our 37, multiplying that by 2, we get 74. Using that same table, we're changing our ideas. So now it's still 6 subintervals. It's a left Riemann sum. So my delta x is the same. But now we're choosing the left sides of the rectangles. Ah. So 1 plus 5 is 6, 6 plus 3 is 9, 10 plus 8 is 18. So we can already, or should already, recognize that the left Riemann sum is going to be less than the right Riemann sum. Just because looking even at these values, the last one's 5 and the first one's 1, so it's less than for sure. So 18 and 9 is 27. Adding 6 more to that, we get 33. 2 times 33 is 66. So we had 74 versus 66. And again, those numbers are 8 apart because 2 times 4 is 8. And the difference between 1 and 5 is 4. And the width is 2. Now to do MRam, when we don't know our function, means that my subintervals have to get larger. So now I'm only going to have 3 subintervals. So my width is 4. So then my rectangles go from 0 to 4, 4 to 8, and 8 to 12. Because now that makes the midpoints of them at values on my table. So the midpoints are going to be at 2, 6, and 10. And we get 64. So the M, L, and R rams all relate to rectangles. So think of ram and rectangle. And while most rectangles are good approximations, there are times when a trapezoid will be a better approximation because it can kind of account for that triangular curved region. So if you think about a trapezoid turned on its side, where its height would be our base or width of our rectangle, aka our dx, we can now kind of average the left and the right bases, but because we're not just looking at the midpoint, we're taking into account that curvature, we'll be able to get a much better approximation of an area under a curve. So what we're going to do is create trapezoids rotated 90 degrees so they're going straight up and down. Anybody still copying that down? I know it was quite a bit of information to copy. So I was trying to give you a little bit of time to write it down. Okay. So for the next example, I gave you the graph so that we could see a trapezoid in action. So it says use 4 trapezoids. So that 4 trapezoids is my n value. To approximate the area under the curve, here's the equation of my curve. So I can use that to find my values on the curve. And my interval is 1 to 3. So that makes my delta x 3 minus 1 over 4, or 1/2. So we're starting at 1. And we're going to 3. So the trapezoids would have a width of 1/2. So this point here would be my B1. This point here would be my B2. And there's my first trapezoid. So I'd need to know f of x at 1 and f of x at 1.5. So f of x at 1, well, 1 squared is 1. 1 plus 2 is 3. 3 minus 2 puts us back at 1. And you could almost have seen that from the graph. But again, you wanted to make sure you did it correctly. 1.5 squared, well, that's kind of like 15 squared, which is 225. So 1.5 squared is 2.25. Add my 2 at the end, so you have 4.25, and then subtract 1.25 times 2, which is like subtracting 3, and we get 1.25. So the area of that first trapezoid would be 1/2 the base, which is 1/2, aka the height, times base 1 plus base 2. The next trapezoid would start back at 1.5 and go to 2. So its height is, for B2, is at 2. So 2 squared is 4. 4 plus 2 is 6. And then 6 minus 4 takes us back to 2. So its area is 1/2, 1/2, and then 1.25 plus 2. Trapezoid 3 would be at 2, and then 2.5. So you'd have 2.5 squared, which is 6.25. Add your 2 to it, and subtract 2 times 2.5, and you get 3.25. And my final trapezoid would be at 2.5 and 3. which is a height of 5. So 1/2 height, starting, ending. So the reason I wrote out each trapezoid was to hopefully show you that parts of the equation repeat just like the rams. So we could think of this entire area, or summation, as 1/2 times 1/2. And then if you add up all those pieces, what you should notice is, since the trapezoids share base heights, your 3.25 and your 1.25 repeat. So that area is kind of like 1 plus 2 times 1.25 plus 2 times 2 plus 2 times 3.25. So anywhere the trapezoid shared a side, you could just double that value. So you'd have 1 plus 2 times 1.25 plus 4 plus 2 times 3.25 plus 5, which is 19. And then you take 19 and divide it by 4, and you get 4.75. The last thing I want to do is compare trapezoids to Riemann sums. So we have one last table example. And we have that this is a 4 subinterval example. And we want to find RRam. So my table goes from 0 to 7. And my intervals are not evenly spaced. So we have 0 to 1, 1 to 3, and 6 to 7. So this is a case where I was saying that you can't do your delta x because my delta x is constantly changing. Is construct 4 rectangles and determine the new widths at each rectangle. So that has a width of 1, this has a width of 2, 3, and back to 1. So to do my right Riemann sum, I have to do each of my rectangle areas individually. So base times height, picking the right value, plus base times height, plus base times height, plus base times height. And again, my units are centimeters per minute times minutes. So that would be 55 centimeters. A left Riemann sum. So my widths are all going to be the same. But now I'm going to pick the left endpoints, so width of 1, height of 1, width of 2, height of 2, width of 3, height of 5, width of 1, height of 10. Okay, 1, 2, 5, 10. JK. I knew that felt wrong. 3 times 5 is 15, not 8. Okay. And then the last one is a trapezoid. So far we have an area of 55 and an area of 30. Those are really, really different. So our area of a trapezoid is 1/2 height b1 plus b2. Since our height is represented by our dx, and we know dx in this case is differing, we can't do what we did in the last example where we factored out the 1/2, 1/2. We can, however, keep the other 1/2 factored out in front and use it at the very, very end. But for this one, my height is 1, and then it's 1 plus 2. Plus my height of 2, 2 plus 5. Height of 3, 5 plus 10. And height of 1, 10 plus 13. So I get 1/2. 1 plus 2 is 3. 3 times 1 is 3. 2 plus 5 is 7. 7 times 2 is 14. 5 plus 10 is 15. 15 times 3 is 45. And 10 plus 13 is 23. So then you'd add up 3, 14, 45, and 23 to get 85, 60, 68, yeah. And divide that by 2. And we get a 42.5 centimeter area. Which is roughly between 30 and 55, if not exactly between them. So we can see how the trapezoid accounts for that missing space or region that we're not getting with the left or the right Riemann sums. So on the next page, I give you a summary for the steps, and then for the rest of your homework, you're doing the 5.1 Riemann sum practice. And then you'd stop when you get to the 5.2 notes. And I don't believe it's out there yet, but I'm going to show or unhide the 5.1 assignment Dropbox for 8:30 tomorrow morning. Have a wonderful day.